Good day. This is Russell Hawley coming to you from the Tate Geological Museum. And today I'm going to address a question that you might have wondered at some point or another in your life, and that is, how do people know how much dinosaurs weighed? You look at dinosaur books, and all the time they're saying, this dinosaur weighed 10 tons, this dinosaur weighed 20 tons. And have you ever stopped to yourself and asked yourself, how do they know that? Can you ask the dinosaur to step on the bathroom scale? No, for a variety of reasons, that won't work. So today I'm going to show you how exactly we figure that out. Now, using this method, the first thing that you need is a scale model of a dinosaur. This looks like a toy stegosaurus, and I guess in a sense it is a toy stegosaurus, but it's not just any toy. This model, which was made by Invicta Plastics for the British Museum of Natural History, was made to a 1/45th scale. That is to say, this model is 45 times shorter from the snout to the tip of the tail than a real live stegosaurus would be. It's been shrunk down 45 times. So if you're going to do this, you can use plastic model dinosaurs, but make sure that they are scale models and make sure you know what that scale is. And if you don't, then later on, maybe I'll show you how you can figure that out. But the Invicta models that were done for the BM&H are 1/45th, and many of the ones that were done for the Carnegie collection are 1/40th scale. So those work for this exercise too. At any rate, so we've got our scale model, and the next thing we need is a graduated cylinder filled with water. So we pour the water in, and what we're going to do is use the principle of volumetric displacement. This was first worked out by Archimedes in ancient Greece. He was supposed to find out what the volume was of a king's crown. And it was an irregular crown with all sorts of fiddly bits sticking out in all directions. And he was having a tough time figuring out how to calculate the volume of the crown. So he went home and he got into the bathtub to think about it. And he noticed that as he got into the bathtub, the water level rose. And when he got out of the bathtub, the water level dropped. And he realized that the degree to which the water level dropped was measuring the volume of his own body. And he said, well, if it can measure an irregular shape like a Greek philosopher, then it ought to be able to measure the volume of the king's crown. Eureka, he cried, which means, I've found it. And then he ran through the streets of Athens naked, crying, Eureka, Eureka. And that's been a tradition among scientists ever since. But that process, working on irregular objects like crowns and ancient Greek gentlemen, of course, will work on an irregular shape like a dinosaur as well. So as we dunk this guy, he's going to displace the water by a degree equal to the volume of the model. So in we go. Hold your breath. And you'll notice that the model floats. This is a bit of a problem because we're not getting the tail here displacing the water. I could just hold it under with my finger, but I want the volume of a stegosaurus, not the volume of a stegosaurus plus a giant human finger. So what I'm going to do is get this wire. I've straightened out a paper clip here. This hardly has any volume to it at all, so that won't affect our measurement very much. And just push this guy all the way down, so now it is completely submerged, plus a tiny bit of wire. And let's see what the water volume is now with this model in it. Can you read that? That's 550 milliliters. So I'm going to write that down. Water volume with model is 550 milliliters. And now we're going to pull that model out. I'll hook him by the foot and tap the excess water off. Shake, shake, shake. There we go. And the water level has dropped, just like the water level in Archimedes' bathtub. And now, where is it? It's down at 500. So water volume without the model is now 500. So if it was 550 with the model in there, and now without the model it's dropped to 500, then what's the volume of the model? Yeah, that's right, 50 milliliters. So that is a model with a volume of 50 milliliters. So if this has a volume of 50 milliliters, and the real Stegosaurus is 45 times bigger, then we just multiply 50 milliliters by what? 45, right? Wrong. Don't forget the square cube law. A full-size Stegosaurus isn't just 45 times longer than this model, it's also 45 times taller and 45 times wider, because these are three-dimensional shapes here that we're working with. So the actual scaling factor has to be 45 times 45 times 45, which is 91,125. I'm not a lightning calculator. I pre-calculated that. I figured it out beforehand. At any rate, so if we take 50 milliliters and then we multiply it by 91,125, then we get 4,556,250 milliliters. So that is the volume of a full-scale Stegosaurus. All right, so what's its mass? Well, we're lucky in this regard because most animals, most land animals have the same density. And in most land animals, it's about 0.9 grams per milliliter. So that's true of elephants, of Cape buffalo, of African lions. And if it's true for all those beasts, it's a very reasonable bet that that would have been true for dinosaurs as well, that they would have had a volume of about 0.9 grams per milliliter. So we multiply all those milliliters by 0.9 grams, and then we end up with a mass of 4,100,625 grams. Yes, a Stegosaurus weighed more than a pile of 4 million paper clips. It's a little inconvenient to talk about grams when we're talking about the masses of dinosaurs, but this is the great thing about the metric system. We can convert to kilos just by moving the decimal point. So, speaking of the metric system, if you don't appreciate the metric system, just try this exercise using fluid ounces and pounds and feet, and I believe you will develop appreciation for how much easier science is when you use the metric system. Either that or it'll drive you completely insane. But at any rate, yeah, easier with metric, no doubt about it. So, 4,100 and some change kilograms. So a little over 4,100 and a half kilograms. And then to get tons, we just move the decimal point again, and we get 4.1 tons. So in other words, a live Stegosaurus weighed just a bit more than an African white rhino.